Okay, it's on. Hey, welcome to this little section. This video segment is going to be covering, Dalton's law of partial pressures. Now, we've talked about that in the gas chapter, but we didn't spend a whole lot of time on it. So I wanted to spend a little bit of time and go over a couple of problems to show you what that would look like. Okay? Now, the idea that Dalton had was that in a container, if you have more than one kind of gas, then each different kind of gas would have its own pressure that it would exert or put on the container itself. Now, the idea behind pressure is force over area. That's the idea. So if I put my hand against the board, for example, I'm putting pressure on there. So in this case here, let's get right to it about the laws of partial pressure. So here we have, if I place 3 moles of N2 and 4 moles of O2 in a 35-liter container at a temperature of 25 Celsius, what will the pressure of the resulting mixture of the gases be? Now, it is interesting to note that there is no at start and that there's a finish. So this is obviously a gas problem. We're looking at the total pressure of the gases. So each gas has to contribute some kind of a partial pressure. But how in the world do you figure this out? Well, we could look at the combined gas law, the PV over T. But here's the thing though, if you look at the problem, there is no beginning and there's no end, which is a key thing when you're looking at those combined gas laws. That's a huge thing. So it can't be that. So what could it possibly be? Aha! It's a frozen moment in time. It's the snapshot. It's the snapshot of the gases. Now what formula have we talked about in class where we deal with the snapshot in gases? Ideal gas law. Yeah, the ideal gas law. So we have here PV equals nRT. Now, a few things. We know our moles, we know our volume, we know the temperature, and we know the R. Okay, now, a few things we need to do. Now, R, it's a constant, okay? 0.082. That's our constant. I'm not worried about units here. We just want to get right to the point. Now, the temperature, well, the temperature has to be in Kelvin. Okay, that would be kind of important because if you look at R, the units of R, it is in Kelvin. So that means we have to change the 25 degrees Celsius into Kelvin. And the easiest way to change Celsius into Kelvin is go ahead and add 273.15. So we're going to go ahead and go 25 plus 273.15, and that's going to get us 298.15 Kelvin. Whoa. There we go. So we know it's Kelvin. Okay? So we know that. So we have our R, we have our T, our V. Ah, yes. Well, that's 35 liters, isn't it? Okay. Now, what we do need, we need to look at the moles of N2 and the moles of O2. Now, we're going to have to do 2 separate calculations here. Okay? 2 separate calculations. So for the first one, we're going to go ahead and we can now plug all this information in. So PV equals nRT, we're looking for pressure. So that means if we look at the pressure, let's look at the N2 for example. The pressure of the N2 is going to equal nRT over V. Now the same thing would also be true for the oxygen. So we've set up the formula, the ideal gas law. Why are we using the ideal gas law? Because there is no beginning and end. We don't have an at start and an end. We don't. We only have that snapshot, the sulfate. Remember I told you about the ideal gas law being a sulfate. All right? So we just go ahead and we can plug all this in. We're going to separate this for a moment. And we can plug in our numbers here. So we know that we're going to have 3 moles, okay, multiplied by 0.082, because that's our constant R. Now that's really important that you use the correct R for the units that you guys are working with. Here's why. Because there are different units of pressure, different units of temperature, and that would be a big deal, because if you plug in the wrong R, you're not going to get an accurate answer. You'll get an answer, it just won't be an accurate one. So we've got 3 moles times 0.082 times the temperature, which was 298.15 Kelvin, and we're going to divide that by the big whopping 35 liters of the gases. So the pressure of the N2, when you go in and solve all that out, is going to be a big whopping 2.09 atmosphere. So that's just the pressure with the nitrogen. Well, what about the oxygen? Well, the oxygen, you're going to do the same thing, right? You're going to go ahead, so we figured out the pressure of the nitrogen. You're going to do the exact same thing with the oxygen. You're going to have the pressure of the O2 is equal to nRT over V, okay? So I have to take a shortcut in the interest of time. The pressure of the O2 is equal to 2.79 atmosphere. Now this is the pressure due to the oxygen. What was the problem asking us? They're asking us for the total pressure. Well, the total pressure is you're just going to add these up. That's complicated, isn't it? So 2.09 plus 2.79 is going to equal the big whopping 4.88 atmosphere. And that, ladies and gentlemen, is the answer for the first problem. Yes! Okay. Now I do need to move on to the next one. Now the next one is different. It's a little bit different. Now we have 2 flasks are connected with a stopcock. A stopcock is basically a valve that will allow the gas to travel through freely between the 2 containers. The first flask has 5 volume liter, has nitrogen gas, and we're going to assume nitrogen gas is N2 at a pressure of 0.75 atmosphere. The second flask has a volume of 8 liters and contains oxygen gas at a pressure of 1.25 atmosphere. When the stopcock between the flasks is opened and the gases are free to mix, what will the pressure be in the resulting mixture? Okay? Now here, we are not looking at the ideal gas law. Well, why? Because we have a before and an after. We have a before with the 2 flasks separated, and of course it might be a good idea to just go ahead and separate the 2. So we have N2 and O2, and here's our tube. Right now it's not connected. Okay? And they're telling me here that I have 5 liters, okay, and it's 0.75 atmosphere. Here for the oxygen, we have 8 liters, okay, and we have a pressure of 1.25 atmosphere. So this is our before. This is our before. Now, we have an after. The stopcock has been released, okay? So now the gases are just freely flowing around in there doing their thing. So now we don't know, okay, what's going to be the pressure in the resulting mixture. So in this case here, we can't use the ideal gas law because that's the snapshot. This is not a snapshot. We have a before and then we have an after. Well, if we have a before and an after, then that means we have to use the combined gas law. The P1V1 over T1 is equal to P2V2 over T2. That's the combined gas law. Now notice I didn't sit there and memorize Boyle's or Charles or Guy-Lussac's. I didn't. I just know this formula. Now what do you notice about the problem here? What about the temperature? Is it constant? Well, they don't mention anything about the temperature. So it's reasonable to say that the temperature is going to be constant. Thus, ladies and gentlemen, I'm going to push this up a bit. We have P1 V1 is equal to P2 V2. So that's what we have. Now, watch this. We're going to figure out the partial pressures of each gas. Yep, and we can do that because we, ladies and gentlemen, have it here. So let's take a look at the partial pressure for nitrogen. So we're going to look at the pressure for the nitrogen. We know at the beginning it's 0.75 atmosphere multiplied by the volume, 5 liters. That's going to equal X multiplied by 8 liters. Okay? That's what you're going to get. So the partial pressure of nitrogen in this case is X equals 0.288 atmosphere. That's the partial pressure. That is the partial pressure for the nitrogen. This is the after because we have the before. Here's the after. And notice how the pressure went down. Well, that would make sense because you're going from 5 liters to 8 liters. Remember that inverse relationship. Okay? We're going to do the same thing for oxygen, but in order to spare time, I'm going to tell you right now that it's 0.769 atmosphere is equal to the pressure of the oxygen. Okay? So at the end, our final answer, we're going to add these up because that's what they want us to do. And our end is 1.057 atmosphere. That's our final thing here, ladies and gentlemen. So that's what we've got for pressure and volume here for this problem. This is our final answer, the combined pressures of all of them. Okay? All right, let's go ahead and let's move on. I do believe we've got one more to look at here. Oh, yes. Okay. So, we have here a situation. We're looking at the partial pressure of carbon dioxide in a container that holds 5 moles of carbon dioxide, 3 moles of nitrogen, and 1 mole of hydrogen, and there's a total pressure of 1.05 atmosphere. So they're asking us the partial pressure of the carbon dioxide. Okay, well we know that the total pressure is equal to the partial pressure of the carbon dioxide and the partial pressure of nitrogen gas and the partial pressure of the hydrogen gas. That's what we have, which is equal to 1.05 atmosphere total. Now the question comes down to is, where do I even start? Do I even need to use the ideal gas law? No. Yes, you have a snapshot. That's true. But at this point, you're looking at the partial pressure for carbon dioxide, and they're giving us the total pressure. We need something else. What could it possibly be? Aha, mole fraction. Keep in mind, mole fraction would be a constant. It's a proportion of how much gas there is in the container. Okay, so what do you do with a mole fraction? What in the world does a mole fraction look like? Well, the idea behind a mole fraction, is really simple. Okay, you are going to take, in this case, the moles of carbon dioxide, which is what we're interested in, right? Because they want the partial pressure, but to get to partial pressure, we need to find out how much carbon dioxide do we have compared to the other gases, compared to the moles of CO2 plus the moles of nitrogen and the moles of hydrogen gas. That's what we have for the mole fraction. So we're going to take the part of CO2 and divide it by the sum total. So this is going to be easy. So we're going to look at the mole fraction This is the formula, by the by. We're going to look at the mole fraction, and that's going to equal, let's see, 5 moles of carbon dioxide. That's going to be 5 over 5 plus 3 plus 1. So that's going to equal 5 over 9. That's our mole fraction for carbon dioxide. Now, they represent the mole fraction with this funny looking X symbol. Sort of looks like chi if you're in AP biology. I'm hearing the groans, okay? But it's not chi, all right? So we're going to look at the mole fraction of the CO2. Now, it turns out once you find, I have to speed things up here now because I'm running out of time. Once you find the mole fraction of CO2, here's the last part that we need because we only got one part left. The last part. We looked at the idea of the mole fraction. We looked at the idea of total pressure and partial pressures, okay? We know that it's 1.05 atmosphere. That's the total pressure. So, if we're looking at the partial pressure of the CO2, that's going to have to equal the total pressure, this is the formula, guys, multiplied by the mole fraction multiplied by the mole fraction of carbon dioxide. Yeah, that's exactly it. So the partial pressure of carbon dioxide is equal to the total pressure that we have multiplied by the mole fraction of carbon dioxide. And in the end, what we end up getting as our final answer is 0.583 atmosphere. This is it. This is our final run here, ladies and gentlemen. And, well, so what did we look at? We talked about the idea of partial pressures combining to form the total pressure. We talked about the idea of the mole fraction, which, again, I gave you guys the formula based off of the formula up there. We looked at a situation where we were allowing gases to mix freely with each other, and we noticed that we couldn't use the ideal gas law because it wasn't a snapshot, it was a before and after. And that's where Boyle's law came in because the temperature was the same. It was constant, which made things so much easier. Okay, and then as we worked our way toward the top here, this one we had to work with the total resulting pressures of everything, and that, ladies and gentlemen, that's when we got to use the ideal gas law. Hey, I'm hoping this helps out. You got the mole fraction, you got the Dalton's law of partial pressures, and, excuse me, you got the ideal gas law as well. The PV equals nRT. All right, take care, guys. Hope this helped you out.